Good day, Math 30-1s. Today we continue our conversation of trigonometric functions, but this time it's a little bit more of a calculator approach. What we've been used to in the past is solving these unit circle or maybe clean amplitude stretches and period changes and midlines, and what we're going to look at today is more real-world scenarios and how do we deal with coming up with equations from maybe limited or different information, and how do we solve on our calculator, because it is still a powerful tool. First thing, just to get us back in our mindset of solving equations, if I asked you to solve 2 cos squared of x equals 1 between 0 and 360, this is a chapter 4 question, 4.4, where we might try to isolate cos of x. First we would divide both sides by 2, and then square root both sides to give us a positive or negative giant square root of 1 over 2. And I'll write that a little bit more cleanly as a cos of x is a positive or negative 1/2. A ratio that should look a little bit comfortable. We know that cosine is positive on the right side and cosine is negative on the left side, because x is positive here, x is negative there, or CAST. They're all here. 1 over root 2 is a 45-degree reference angle, and this gives us 4 answers between 0 and 360, 45 degrees, 135 degrees, 225 degrees, and 315 degrees. Notice how that second number from the right, 4, 3, 2, 1, just keeps shifting down because we're adding 90 degrees each time. Now, if we were solving this graphically, it might seem strange because we can do this algebraically, but not everything is going to be convenient, but let's start out with a comfortable approach. When we're graphically solving 2 cos squared equals 1, we can really approach this in 2 different ways. What we can do, and we've done this before in previous grades, starting in chapter 10, is graph the left side as y1 and the right side as y2. We're going to graph this as a system. So in our calculators, we're going to be saying 2 cos squared of x, 2 cos squared, and all of a sudden you might say, well, how do I put that squared in there? That seems a little strange. What makes people feel a little bit more comfortable is to create a bracket and say, let's just say cos of x, close a bracket, and now we've basically said cos of x is within its own bracket, and we can square that bracket around a cos of x. And this usually gives people a little bit more comfort. So we're saying when is 2 cos squared y1, and when is 1 our second equation? Now I really don't know what 2 cos squared looks like. Does it go up to 1, down to negative 1? Maybe not. But what we can do is make sure that we're in a mode that makes sense. And this question currently says between 0 and 360. So we're going to set our window to go between 0 and 360 and be in degree mode. So 0 to 360, maybe a 45-degree scale. And y min to max, again, not really sure where this goes, but I'm going to say from negative 1 up to a 3, only because I see one equation is going to have a 1 shooting across, and so maybe there's stuff above or below that. So as we graph this, we can see what it looks like. And in fact, it was a decent guess because negative 1 to 3 does put us very much in a middle. So I'm going to sketch this on my grid here. I know that I had my axes there, and we're basically drawing as best we can what seems to be happening. And if we're trying to find when these functions intersect, which looks like it's 4 times, we can say second trace, number 5 intersect. First curve, second curve, and I'll just find the second one, which conveniently is 135. So this is 45, 135, 225, 315. This is all very symmetrical, right? It's because every 90 degrees we're getting an answer. So the answers again are 45, 135, 225, 315. This is nothing very impressive, but it's all kind of the same thing. Now I won't do this as detailed for the second one, but there is another way we could get these answers. Choice B could say that we take everything over to one side, 2 cos squared of x minus 1 equals 0, graph the left side as y1, and basically determine the zeros. So you could essentially not say equals y1, but equals 0 by saying subtract 1. And this might look different. We are really just shifting everything down 1 and saying when does it meet 0, but these intersections will be the same. Instead of doing a second trace 0, I could, but I have another equation here that's 0, so I could really just do another intersection of the function and y equals 0, because I do have another equation in here, y equals 0, and see when they meet. And 225 is another answer, which kind of confirms we're getting all the same things. So you could either move everything over to one side and find your zeros, or find when the left and the right side intersect, but it all does the same thing. So we sped through that one, and we'll start to maybe approach some more complex functions. Now, if we had something maybe a little bit different, and maybe doing this in radians, we could see how things might feel slightly different. Now, if you were to do this algebraically, you would again isolate your trig statement. Sine of x would end up being add a 3 over, divide both sides by 4, square root both sides to give us a positive or negative square root of 3 over square root of 4. And we could find these answers out quite quickly where sine is positive, sine is negative, at a 60-degree reference angle because we remember the unit circle. And we've got our 60, our 120, our 240, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, and our 5 pi over 3 answer. Now, in our calculator, it's not going to be able to tell us exact answers, which is also a bit of a limiting resource, because the calculator won't really maybe give us as precise an answer as we want. If we do type in our left side for sine squared minus 3, right side as 0, we can sketch what this looks like, and we'll probably have to be careful with the window settings because we're saying some things going down 3, so let's change our window settings to go between 0 and 2 pi from negative 4 to, let's say a 1, and make sure we're in a radian mode. So it was radian mode, 0 to 2 pi, and a bit of a vertical shift in our scale. When does this intersect 0? We've got 4 answers, 1, 2, 3, 4. Second trace, number 5, intersect. First curve, second curve. And I'm going to get our second answer, 2 pi over 3. What's it going to say? 2 pi over 3. About 2.094 radians. That is a limited answer. Now, this is your pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Things are not as symmetrical. What starts to happen is when we want to get maybe general solutions, which we're going to approach next, we have to start considering how do we say all these answers if we didn't limit our domain from 0 to 2 pi. It's important to say that this answer, right here, pi over 3, and as you follow along, and this answer are a full wavelength apart. So I could say that from 0, from pi over 3, add a 2 pi, add a period, and you get to another answer. Add a period, you get another answer. From this one, add a period, you get an answer. So each of these two results, you could add a period to and get to more answers. And this is what we're going to approach next. Solving a general solution, this time when you look at an equation like this is not a question we're going to attempt algebraically. This feels very much like a 5.2 graphing question, and that means we're going to approach this as a 5.4 calculator graphing question. This doesn't feel like a chapter 4.4 solving equations using the unit circle kind of an example. This looks more like a B, D type of question. And so if we graph this in our calculator, we're going to do this in radian mode, where we've got 16 as one side, and we've got 6 cos of pi over 6 x plus a 14 as the other side, and a window setting that I've given us because I noticed that midline is 14 and we're going up 6. So the max is about a 20, and so I was saying, well, let's go up to about a 22 for our max, for y. I know that from 14 going down 6 puts us at about an 8, so I said, well, let's go down to about I said -2. It might be a bit extra. For y values, we're saying go between -12 to a 12. For a scale, 2. So x min, x max, x scale, y min, y max, y scale. Mode is in radians, and we can graph. There's your 16 that shoots across, and there's your graph. Again, I had way too much extra down here. And this is roughly what this looks like. So as we sketch, I'm right-handed, our axes. Ooh. To determine these 4 answers, we're again going to be asked, what is the general solution? So if you find a couple of these answers, like second trace, intersect, first curve, second curve, guess, I'm getting for this one a 2.35. Second trace, intersect, first curve, second curve. If I find the one that's further along on the right, the next positive one, I could say 9.65. Where will the next one be? Well, if we take 2.35 and do a full period, we should get to the next answer. We return back to the original position. So I think we have to ask then, what's the period? Because it's not always 2 pi if there's maybe a b value. So the period for this question in radians is 2 pi divided by pi over 6. Pi's cancel. 6 times 2 gives us a 12. The period is 12. One of our answers starts at 2.35, and we add a full period and any multiple of those periods infinitely to the right or the left. Our second answer was a 9.65, and we can add a full period and any multiple of it to the left or to the right. And these are your 2 answers which give you all answers. And this is a really tough question, solving a general solution where there's a period change, but this is a bit of an intensive one where it's, again, not solving this algebraically, but graphically. So this brings us to our last kind of conversation, and this is as we get into applications. Now, applications we're dealing with anything that's cyclical, anything from the phases of the moon, the temperature over the course of the year, the tides rising and falling, or even something as simple as a Ferris wheel. Now, a Ferris wheel is a really good example to transition with because we're really talking about a circle and maybe someone going around a circle, which is tying into our unit circle conversation. So let's say we get limited information, like you get on a Ferris wheel 2 feet off the ground. So let's say this is 2 feet off the ground, and we're going to draw a bit of a picture as we do this. 2 feet off the ground, you get on a Ferris wheel at the bottom, and the time 60 seconds to make a full revolution. So you travel up, and you come back down, and that took 60 seconds. The Ferris wheel advertises a max height of 52 feet. It's important to remember that when we're drawing sinusoidal functions, that everything is broken up into halves and quarters. If it's halfway in between to the max, it's also a halfway in between, which isn't perfectly symmetrically drawn, halfway to the midline. Another halfway to the midline. Where is the midline? Well, where's the average? This all of a sudden gets us thinking about, well, what are some values here? At a time of 0 seconds, we're told to be getting on at the height of 2. At a time of 60 seconds, we made a full revolution and we're back to a height of 2. Halfway around, we were at our maximum height of 52. Quarter-way and 3/4-way points, our height was somewhere in the middle. Well, what's in the middle of 52 and 2? That's thinking about the midline, the d value. This is your average of max plus min divided by 2. Max plus min, 52 plus 2. Your d value is going to be at 27. This is the height at your crossover point, 27. So that's the height at the quarter and the 3/4-way point, there and there. So 0 seconds, 15 seconds, 30 seconds, 45 seconds, 60 seconds back to the beginning. Everything is broken up into quarters. So we already have a d value. We could go and ask, well, what's our amplitude? This is all stemming from our 5.2 lesson, where the amplitude is the total distance, not negative, the total distance from the top to the bottom broken in half, which gives you the distance from the middle to the top. Max minus min divided by 2. 50 divided by 2 gives us an a value of 25. That makes sense. 2 and 25 is 27. 27 and 25 is 52. Our b value stems from our advertised 2 pi divided by 60 seconds, which reduces down to be pi over 30. You might ask, well, how do you know it's not 360 degrees divided by 60? Well, I was highlighting this earlier and didn't mention it. Whenever you're doing application questions, you will always be in radian mode. One more time. Whenever you're dealing with applications, you will always be in a radian mode. Much of your test, you will be in a radian mode unless a question starts asking about degrees. So we have our A, we have our B, we have our D. What could be our equation? Well, C value is the last thing. C value as a cosine graph maybe starts at the max at 30 seconds. Maybe as a cosine graph flipped upside down, you say it starts at 0 and there's no shift. Maybe as a sine graph starting upward, you're at 15 seconds. There's actually many answers to this equation. So you might say as an equation, we've got an a value of 25 as a sine graph, b value, x minus, now we did say a sine graph starts on the midline traveling up, so you're starting at 15 seconds. Instead of saying radians, I get to say seconds now, and a d value of 25. We could have also said as a cosine graph, 25 cos of pi over 30, starting at the maximum, which was 30 plus 27. But to be honest, neither of those are probably the one that I would have selected. I would have said negative 25 cos of pi over 30 x with no shift, but flipped upside down because we're starting at a minimum. So because we're starting at a minimum, I can say there's no shift, we're just flipped upside down. This means there's a little less danger in putting stuff into our calculator and making mistakes. Our final two questions are really what things boil down to. What's the height 12 seconds in? When am I first at a height of 35 feet? 12 seconds in, what's our height? I'm going to guess it's about a 5-ish. And 30, when are we at 35 feet? Probably about 17, 18, 19-ish seconds in. These are the kind of questions we're being asked, which we can't do unless we have an equation. So this becomes a calculator approach where we can type in our equation and we're asking for either inputs or outputs. So I'm going to type in the negative 25. I'm going to use the cosine one, which has less potential for mistake. Pi over 30 x plus 27. So we're flipped upside down. We are inserted flipped upside down with a 25 cos. Good. So making sure my window settings make sense, I'm going to go from 0 to 60 seconds. Every 15 seconds could be a scale. And going from the ground up to our advertised max of 52 feet. And we should see this as long as we are in radian mode. One perfect path around our Ferris wheel. What is the height 12 seconds in? Second trace value. 12 seconds in, we're at a height of 19.27. 12 seconds in, right about here, we're at a height of 19.27 seconds in. At 12 seconds in, we're at 19.27 feet. How do we get 35 as a y value? How do we get our x value? Well, this is where we have to go and make a brand new equation and say, when is our path going to reach 35? This is a second trace intersect. First curve, second curve, bit of a guess. And after 18 seconds, we reach our height of 35 feet. I've seen questions that ask for how long are you above 35 feet, and then maybe you're asked to find a second intersection and then determine that time period between. So there's lots of little extensions that we can have, but at this point we're starting to see that we're being asked to make a question and then determine something very specific which you could never guess without an equation. It's really just an extension of our previous understandings. So at this point, it's a bit of practice, and I wish you good luck as we investigate applications of sinusoidal functions. Good luck.